that's usually, as long as you buy in and you pay attention and you practice well with your homework, it's usually a pretty easy test, which is nice, especially in comparison to the vector test. So as you're doing vector corrections, you're like, matrices, whew, okay. Especially because I know Mr. Trey did a great job of at least introducing them last year. So, matrices. The first thing that we need to review with matrices is, well, actually not where notes start. Okay. Matrices time. Okay. Where we start is, technically what I wrote down, it's an application, or I should say it's a means of solving systems of equations. It's a great means. It's actually a technological means. Matrices, there's this class in college called linear algebra. It's required for anybody who's computer science, anybody who's engineering, anybody in the math sciences. It depends, only if you're going like in a techie science type direction. What else? Engineering, business, maybe linear algebra, but definitely anything to do with computers, anything to do with math. So matrices, we're kind of still trying to, and we started it in section 7.3 last chapter, when I was talking about, like, okay, the stair step, and if you could tell a computer to do this every time, we don't care about how messy the numbers are. Okay, but we're humans, and we get to kind of use our tricks to get there. But still thinking of a system, a procedure, kind of getting you closer to a program-ish that you can use technology to do for you. Matrices, we're kind of going to be dealing with that too. It's a whole other way of organizing information. And yet it will look similar at times. So this whole substitution, elimination, row echelon form, they're all going to kind of come back in bits and in pieces, but matrices is, as you guys know from last year, some sort of rectangular array. I asked you guys to find it in your calculator to review a couple things about these little symbols down here below, okay? Where'd you find it? Where are matrices? Second, x to the negative 1. Hey, x to the negative 1, isn't that like a inverse button or a, What's the negative 1 button do? What's the negative 1 button do? Reciprocal, yeah. Why am I doing that? Well, remember that log and 10 to that and ln and e to that? Like there was meaning as far as what was above and what was below. Some of these are tied together. I wonder if reciprocal has anything to do with matrices. Anyway, keep that in the back of your mind. But for right now, yes, you were right. Second, x to the negative 1. How do I put a matrix in? Because if I just hit enter, it just says, okay, cool, there's an A. How do I put a matrix in? Edit. Good. Oh, that makes sense. You're editing a matrix. Okay, cool. What's the 3 and 4 stand for? Oh, hey. Look, order, a number by a number. It looks just like that. So what's the 3 and what's the 4? 3 is how many down, yeah. And 4 is how many over, like Sway's right, like how many down, how many over, but what's the snazzy way of saying that? Rows and columns. Got it, let's label. Okay, so the first number that you have in an order, that's how many rows. The first number in an order, that's how many rows. The second number, how many columns. The first number, how many rows. The second number, how many columns. And when we're talking about something like AMN, if you were in your calculator, and if you were to go down, let's go past the 3, past the 4. Do you guys see this notation that your calculator is showing you? Matrix A, this would technically be a subscript if it could show it to you, but there's not enough room, I could say, to show it to you in this field. It would be a subscript. It'd be A little 1, 1, and then I have A little 1, 2. Oh, went the wrong way. 2, 1. 1, 2, 1, 3, 1, 4. What do those little numbers stand for? And then 2, 1, 2, 2, 2, 3, 2, 4. Yeah, it's the exact location, right? As far as which, oh hey, it acts just like this one. Which row, oh that's why it's M. Which row and which column. So this little guy is what we call an entry. It's an entry in the matrix, A11, A12, A13. Now in your calculator, it shows it in that little like function notation kind of sub 1, 1, A of 1, 1, A of 1, 2, A of 1, 3, but we just make it simpler than that. We do a lowercase talking about the guys inside the matrix, not the big guy who's the name of the matrix. And then we just put the numbers right next to each other, which Honors was like, well, what if there's like 10 rows? Is it going to be like 10, 1? That's awkward. It's 101. It's kind of like we're not going to deal with too big a matrices anyway. And in the calculator itself, where it's actually involving the programming, etc., it has it delineated so that it won't be confused. But for us, 1, 1, 1, 2, 1, 3, 2, 1, 2, 1, 2, or 2, 1, 2, 2, 2, 3, etc. Just when you see this, don't think 12, don't think 13. Think of row and then column. And we're not going to get big enough that it gets that confusing. And so partially what you can be thinking of is kind of like Battleship. Why? Yeah, when you're trying to get hits, when you're trying to guess the location of your opponent's ships, if you've ever played Battleship, you have to actually like talk about the grid and talk about the over, talk about the up, talk about the rows and the columns, etc. So it's kind of similar to that in the sense of how we're naming, how we're discussing matrices, but it's not like Battleship in that Battleship has like in different places on the grid, some things are filled in, some things aren't. Matrices, it's like, no, we fill in all the fields. But if there's nothing there, we put a 0. So I guess you could kind of do that with Battleship. But rectangular arrays of all different shapes and sizes. Thinking about what you guys just saw with the order, like a 3x4 and what that looks like, what would be the order of letter A? Yeah, just a simple 1x1. And who would we call that to? A11. First row, first column, that's all there is. Kind of boring, but there it is. Letter B, what would we call it?
1x4.
A 1x4. A 1x4. 1 row, 4 columns. And if we wanted to, we could go ahead and name each of these to be A11, A12, A13, A14. Right? First row, first column, second column, third column, fourth column. How about C? This is our first introduction to a square matrix. Any square matrix is one where the rows and columns are the same. We've already talked about the first row and how to name those, so let's just make sure we know how to name the second row, the A21 and A22. Not 22, not 21. The 21, the 22. Little subscripts just telling you where the guy is. How about letter D?
3.
How many rows? How many columns? Now, what's great is if you have your calculator, couldn't you go make a 3x2 or a 2x3 and make sure you're right? Yeah. But also begs the question that Nikki already asked. So is this next test all calculated? The answer is no, but half-ish like yesterday. Half-ish like yesterday. So some things to learn for sure, some things to be able to do without the calculator. But man, if you're using the calculator, use it to its fullest extent. Don't ever be confused on order. Go make one and make sure you have the right size. So that's why I want you guys to keep this calculator close, because we're going to try to be learning it, and not just learning what it does, but also maybe some of the programming behind what it does and how it's being told to do what it does. That was kind of complicated. Sorry. Okay, just naming the order, knowing what size it is, using the rows and then the columns. Are we good? So then, a couple quick vocab. That guy who only had 1 row, he's actually called a row matrix. 1 by whatever, 1 by 1, 2, 5, 10, a million. Still just has 1 row, he's called a row matrix. If it was going the other way, we would call him a column matrix. You would have however many rows you want, but still just 1 column. And we kind of talked about that square guy, where you could make it an m by m or an n by n, the number of rows or the number of columns, the number of columns, and the number of rows. Then we have this special guy down below called an identity matrix. Square matrix. The leading diagonal of ones, however long you want to go. And everybody else, how does it go? Keep on going, have a leading diagonal of 1, everybody else here. Whenever we hear identity in math, it's talking about some sort of value or some sort of, quantity. With numbers, that's pretty much the only time you've seen identity thus far, unless it's like an identity that you memorize, like the trigonometric identity. But the identity for numbers is a value that preserves the quantity, the value, the identity of the original given expression, number, function. So the multiplicative identity of any number. What's a number that you can multiply and still preserve the identity of whatever it is you're multiplying by? Its identity remains unchanged when you multiply by it. 1. Yeah, 1's the multiplicative identity. Multiply anything by 1 and it stays the same. How does that become important? I don't know, common denominators? As long as I'm multiplying by 3 over 3, 5 over 5, 10 over 10, I'm not changing the identity, the value, the worth, the magnitude of the original. I'm just changing what it looks like, but I'm not changing its core value. I'm preserving its identity. So we use that whole the multiplicative identity of 1 in a lot of different ways. Whenever we multiply by 1 creatively, whenever we make sure we multiply the top and the bottom. Hey, when we were simplifying complex numbers and multiplying by conjugates, that was because of the multiplicative identity of 1. What's the additive identity of numbers? What do you add to numbers and still have it preserve? Yeah, 0. Add 0, stays the same. Which, for you guys, I don't think we've really used tons and tons and tons, but that whole thing that John and I were talking about in Calc BC, that partial fractions is useful for, that whole crazy thing. There's a time when we actually have to say, we don't have what we want. Some of you might have done this in T-proofs, but you would have been starting on the sides that were the weird sides. There wasn't a lot there, and you had to create what you wanted instead of just work with what you already had. If you're creating, sometimes in order to create and remain balanced, you have to think about the 0 thing. Okay, well, hey, complete the square. If you add something here, you have to subtract it somewhere else. There's that whole idea of adding by 0 creatively, multiplying by 1 creatively, adding by 0 creatively. Anyway, there are further applications of this whole additive, multiplicative identity with numbers, but now we're with matrices. So it begs the question, well, how is this guy the identity of a matrix? Well, we have to kind of talk about matrix operations, like how you add matrices, how you multiply matrices to figure out why he's the identity. For right now, he's just the identity. We'll get back to him. We're going to talk more about matrix operations, but I just kind of introduced addition, multiplication, how vector dot products kind of tie in with matrices. That's a whole weird thing. But that's going to be section 8.2. So some of you that are like, I was ready for matrices. Let's just do some adding, some multiplying. Let's do the basic stuff from last year. That's 8.2. So that kind of begs the question, what's 8.1? What was the title of this again? Systems of equations. It's matrices applied. How do matrices apply to help us with systems of equations? Ready? A matrix can be derived from a system, or even better yet, is a way of organizing a system. And I know, as you're writing down this information, you're going to look at that little 2-equation system and be like, we just did a test on it. Why not just do elimination? But remember, we start with something easy, something basic, to get the idea of a tool that can be used for way more complicated things. So yeah, a 2-equation system can definitely be solved in a faster way. You're a human. You can look at this and be like, multiply the bottom by 2 and add. But what if this had an x and a y and a z and a w? 4 variables, 4 equations. Well, your little baby trick isn't going to be quite so little baby, fast, short, and simple and sweet. Man, I'm trying to do way too many adjectives. It's not going to be near as nice as this guy is. Okay, no big deal. Fine. Annoying, but fine. Section 7.3, stair step. If we had an X, a Y, a W, sorry, X, Y, Z, W, just bring in another letter. Don't want to go to A's. If I had an X, Y, Z, and a W, fine, I would do the stair step, and I would go ahead and I'd make the little stair step, back substitute, da-da-da-da-da-da. It even says back substitute. You could have done it last chapter. Yes, you could have, but would you have wanted to? Bless you. Probably not, which is why on the test I made a very clear point to tell you the biggest it got was a 3 by 3, right? So you didn't even have to worry about a 4 by 4, 5 by 5, 6 by 6. The cool thing with matrices is they say, give me anybody, any size, and I can deal with it. Bless you. Give me anybody, any size, and I can deal with it. Okay, here we go. This thing called Gaussian elimination. Ooh, that's way too zoomed out. This thing called Gaussian elimination. Row echelon form. We've already seen that. I know. Let's see how it applies to matrices. Let's take this system and let's make an augmented matrix. Augmented matrix is basically, we haven't covered matrix multiplication. Maybe a few of you remember it. Long story short, we can make this kind of crazy jump where we take out the 8, the -4, the 5, and the 2. Just kidding, we're actually not taking them out. We're actually taking out the x, y from both, undoing a matrix multiplication, which is only legal to undo if all the variables are lined up and even. If I can factor out an x, y, I get these variable coefficients. Now, we haven't done matrix multiplication. I know, I'm jumping ahead just a bit, but I know you saw it last year. Matrix multiplication had this weird over and down thing. It's a dot product. This weird over and down thing, it's a dot product. Anyway, I took away the x and y. Long story short, when it says to make an augmented matrix, it says, okay, take all those coefficients, take all those answers, and mush them together. So I have this nice little square matrix showing me that I have a 2 by 2. I have 2 equations with 2 unknowns. Life is good. It's going to work. But I'm going to go ahead and augment that with the coefficients, or the constants, I should say, on the other side. All of a sudden, I've taken my system and I've basically made it into a matrix. What size matrix? A 2 by 3. So how do I get this stair step with it looking so much different? Well, kind of using what we did before. Just going to be playing with numbers. We're not even going to have to be rewriting this system over and over and over again. I don't do that weird, like, hey, 1 and 2 and 3 and 4 and 5 and ugh. I get to just look at this and say, you know what? Here's what I want to do. I want to go ahead and work by columns. Starting with the first column, moving to the second, and then not to the third. I only have to make it through these little variable coefficients. First column, second column, if it was a 3 by 3, third column. Work through the coefficient columns. One column at a time, and I have to get that entire column good to go before I move on to the next. I'm working by columns starting at the first. When I'm in a column, I'm going to establish the 1. I'll show you at the end how this ties into 7.3. But we're going to establish the 1, and my hint is multiply by the reciprocal. You can also think of dividing, if that helps. You can also think of dividing, but sometimes multiplying by reciprocal is easier. Let me show you, let me model that for you as to what that would look like. If I was to want to get a 1 in the very first column in this very top spot, I would go ahead and I would multiply that entire row, which is row 1. I would multiply that by 1/8. So I'm taking that, if I was to make this like super snazzy and make it all technical, the book would like write a sentence, you know the book, like Calc Chat. I would just go ahead and say, I'm taking 1/8 of the old row 1 and putting it in the new row 1. And so I'd have 1/8 times 8, 1/8 times -4, and then 7 times 1/8. And I've just gotten my 1. If you're curious as to why I got the 1 there and not down below, think of your row echelon form, where we wanted a 1x with stuff, a 1y with stuff, a 1z with stuff, and that was how we got our stair step. You can think of it that way. I want the 1x. But to be row echelon form, I need it to step down. And if it steps down, then I need to go ahead and get a 0 in all the other spots of that column for it to actually fit that stair step pattern. So how do I get a 0? Well, first I got the 1. Check it. I have it. Good. Now I need to get zeros everywhere below. And so the zeros below, I'm going to multiply the guy with the 1, which is row 1. I'm going to multiply him by the opposite number, by the opposite of whatever entry I have in row 2. So the nice thing is I can always, there is a system, I can always take whatever row I got the 1 and multiply it by the opposite. Well, the negative of 5 is negative 5 times row 1. Wait a minute, I don't mind row 1. Row 1's actually good the way he is. He has his 1, he's done to that first column. I need to change row 2. I'm going to multiply row 1 times negative 5, add it to row 2, and put it into row 2. So whenever you're doing these little baby formulas, you're saying, okay, look back and take whatever's in the row 1 spot, and then go ahead and do this operation and move it into the new row 1. Look back, take whoever's in this previous row 1, row 2, do this operation, then move it into the new row 2. What does this do? If I take row 1, each entry, and if I multiply each one by negative 5, negative 5 times 1 is negative 5 plus 5. Got my 0. Those of you that are good with numbers, you're going to get to where you can just fly through these. When you get fractions, they get messy. But those of you that aren't so great with numbers, let me show you what I'm actually doing. Because in your homework, or even on like a test, when I ask you to do a row echelon or a Gaussian elimination one by hand, you don't have to make it all nice and neat and pretty like mine. You can technically take off to the side this little baby formula and be like, okay, hold on, I need a little more space to do this. So I need to take, let's see, this row 1 and multiply everything by negative 5. So I have negative 5, I have 5 halves, I have 35 eighths. Okay, I multiplied everything by negative 5, by negative 5, by negative 5. Negative 5. And I'm going to add it to the second row, which is 5 and 2 and 1. Negative 5 plus 5, 0. I would have done mental math, and I would have done like, hey, that's positive 5 halves plus 4 halves. Common denominators, yeah? Make it easy on my brain. Positive 5 halves plus 4 halves, I would have put 9 halves. But a lot of kids would get, a lot of people would get stuck in that math and be like, wait a minute. So over here, you could take your time and say, okay, wait, I got this. So I have 5 over 2 plus 4 over 2 is 9 over 2. You can take time off to the side. Which is why I advise for people in your homework spiral, you can do your homework here on these, and you can show your scratch paper on like the page before. You can flip it, you can do your work, you can do your scratch work. I've had people also do it on like whiteboards, etc. That doesn't eliminate the need to show this. It just gives you a place, a chance, a space to go ahead and work it out. But you're basically doing elimination. Basically. You're doing elimination. You're trying to cancel out those first two by multiplying in a way that you can cancel out those x's. And then the last one would be negative 35 eighths plus, I would have thought 8 over 8, and I would have done some mental math to get negative 27 eighths. Kimia, you had a question. Sorry, kid. What's that other one? Okay. Remember, we're doing this easy one, this more complicated way, which will work for harder ones. I'm trying to understand some of the programming of those matrices in your calculator. Do I have the first column good? Yes. Why? Because I have a 1 in the x spot, which is what I want. And then I have zeros. Well, I only have 0 here, but whatever side this is, I could have gotten zeros for everybody using this exact same technique of who's in the spot that you want to be 0. Multiply that by the opposite and add. And just do that for the entire set of numbers in each row. Now wait a minute, I'm working by columns. My first column is good. It's time for me to move to my second column. Now as I'm getting ready to move to my second column, now what's that?
Once you got your first column with a 1 in it, and then you multiplied it by negative 5 to get the 0 in the other slot.
Right.
Why did it not stay as negative 5 if you multiplied it? Why is it still 1?
Oh, because I'm only affecting the second row. So this result is going into the second row. I'm not touching him at all.
But you're using...
I'm using him, but that's kind of the joy of matrices, is that I'm not changing the identity of row 1. I'm using him off to the side, and I'm making him whatever multiple I want, but then when I come back in, I'm only affecting that second row. Because I could have had it be 5, but if so, then I'm going to mess up my row echelon. Oh, second column. We got the 1, we got the 0. Second column, it's time to get the 1. How do I get 1s again? Multiply by the reciprocal. Oh, who's the reciprocal of 9/2? 2/9. And the nice thing is, if you do this column by column, the 1s and then the 0s, check it. Is my 0 going to get screwed up when I multiply by 2/9? 2/9 times 0 is still, he's still there, just like I need him to be. What's 2/9 times 9/2? Perfect. What's 2/9 times negative 27/8? My mental mathers are like, oh, sweet, 2 and 8 reduced, 27 and 9 reduced. And I end up with negative 2/9 times negative 27/8. Negative 3/4 this time. Then in my top, I have 1, negative 1/2, and 7/8. Now at this point, I am technically in what we call row echelon form. Because row echelon form says, after doing just that, what you would end up with is your matrix can tell you what your system would be in a way that you could just do a back substitution and be done. Row echelon form. I have it in a way that I know one variable and I can back substitute and I'm done. So I could go ahead and say, hey, I know y. Y is negative 3/4 based on that 1 being in the y column. 1y is negative 3/4. I can plug that back in and I could get x minus 1/2 times negative 3/4 is equal to 7/8. Ew, gross, except that's a 3/8. I can add it to be a 10/8, and x ends up equaling, mental math, there's 5/4. However, even though that was, all well and good, we still had to go back to a system, and we still had to solve. And if this was like a 3x3, a 4x4, a 5x5, that back substitution would be a pain. So what if we just went one more step and said, I wonder if there's a thing where you keep going. You don't just go to row echelon form, you go to reduced row echelon form. What if we went ahead and got a 0 in the other place and got all the way to an identity matrix? 1/2 row 2 plus row 1 into row 1. What if we took that established 1 that we just got, we multiply by the opposite and add? This guy stays the same, Keegan, kind of like your question. We're not affecting that second row, even if we're using a multiple of him. 1/2 times 0 plus 1 is still 1. That stays the same. 1/2 minus 1/2 is 0. And negative 3/8 plus 7/8. Ooh, did I get off? Did someone find a mistake? 3/8. Oh, minus. I added instead of subtracted, didn't I? Did anybody catch that mistake? That's a positive 3/8. 7 minus 3/8 is 4/8. 4/8 is 1/2. Man, I do better with matrices than I do with simple math. Plug it in. I get negative 3/8 plus 7/8 is 4/8. All I had to do was one little baby step in my matrix to get to my final solution, as opposed to writing out a whole system and doing a back substitution. If I had just kept going and not just gotten the 1s and the 0s below, but also the 0s above, hey, check it. 1x is 1/2, and 1y is negative 3/4. What did we just do? Took a simple one. But you could have solved another way. But realize how matrices, with these little operations of getting 1s, they're called row operations, getting 1s and getting 0s. If we just get these coefficients down to the identity, all of a sudden we know the identity of the x and the y and maybe the z and the w and maybe the a, b, c, d, however big this thing might get. without having to figure out how to do stair steps or something that's a lot bigger than what you saw on this test. Alright, so kids, I'll see you tomorrow. This is a 3-dayer. Not due till Monday. You guys can play with test corrections or you can start doing your homework either way. But we'll keep going tomorrow. Some of you might just take a night off of math for your heart and soul mental health night. Bye, guys.